You are looking at a mountain in Iran. There is nothing there. No buildings, no roads, no activity. Just rock. The satellite sees nothing. The radar sees nothing. The naked eye sees nothing. Underneath that mountain, 80 meters of solid granite below the surface, Iran spent 25 years building a nuclear facility specifically designed so that no weapon on Earth could reach it. They did not hide it with camouflage. They hid it with physics, with hundreds of meters of rock that absorbs, deflects, and destroys any bomb before it reaches the target below. But here is the problem Iran did not fully solve. You can hide a facility behind rock. You cannot hide the fact that the facility exists. Not completely. Because everything that operates underground, every machine, every ventilation fan, every generator, every footstep, sends signals upward through the rock. Tiny signals, almost undetectable signals, but signals. Welcome back to Grand Structures. This is how Israel sees through mountains, and why Iran's most secret facilities were never as invisible as Iran believed. The single question this video answers: how do you map what is inside a mountain from the surface without drilling a single hole, without entering the country, and without the occupants knowing you are looking? The answer uses 4 completely different branches of physics simultaneously, and each one exploits a different weakness in the mountain fortress. Let us go through them one by one. Here is the first physics problem that every underground facility cannot escape. Rock is not silent. Rock transmits vibration. When you run a generator underground, it vibrates. That vibration travels outward through the surrounding rock in all directions as a seismic wave. By the time it reaches the surface, it is extremely weak, millions of times weaker than an earthquake, too weak for a standard seismometer to distinguish from background noise. Israel's solution: arrays of ultra-sensitive seismic sensors placed at multiple points on the surface above a suspected facility. Not one sensor, many sensors positioned at known distances from each other. Here is the mechanism that makes this work. When a vibration source, say a generator 80 meters underground, sends waves upward, those waves reach each surface sensor at slightly different times. Sensor A, directly above the generator, receives the wave first. Sensor B, 50 meters to the east, receives it slightly later. Sensor C, 100 meters to the north, receives it slightly later still. A computer analyzes the time differences between all sensors simultaneously and triangulates the exact position of the vibration source underground, not approximately, precisely. The same principle as GPS triangulation, but using seismic waves instead of radio signals. Oh, that is the insight. The mountain is not a shield against seismic detection. The mountain is the detection medium. Every vibration source underground uses the rock to broadcast its own location. The denser and more consistent the rock, the cleaner the signal transmission. Iran built their facilities inside granite mountains specifically because granite is hard to bomb, but granite is also an excellent conductor of seismic waves. The shield became the antenna. A ventilation fan running at 60 cycles per second produces a distinctive seismic signature, different from a generator, different from human footsteps, different from a vehicle. An experienced analyst reading a seismic array output can identify not just where the facility is, but what is operating inside it. Is the ventilation system running? How many generators are active? Is there vehicle movement? The facility is broadcasting its operational status through the rock continuously, whether it wants to or not. The second physics problem that underground facilities cannot escape: temperature. Everything that operates underground generates heat. That heat has to go somewhere, and wherever heat goes, it changes things. Standard thermal imaging cannot see through 80 meters of rock. The heat dissipates too much over that distance. But synthetic aperture radar, SAR, does not look for heat directly. It looks for what heat does to the surface above the facility. Here's the mechanism. When a facility underground generates heat, that heat slowly conducts upward through rock. It raises the temperature of the rock above the facility by tiny fractions of a degree compared to the surrounding rock. Warmer rock expands very slightly. We're talking about fractions of a millimeter of surface deformation, completely invisible to any camera, any human eye, any conventional sensor. SAR satellites emit radar pulses toward the Earth's surface and measure the exact time it takes for the reflected signal to return. By comparing multiple radar images of the same location taken weeks or months apart, a computer can detect surface changes of less than 1 millimeter. The area of rock directly above an operating underground facility shows a distinctive deformation pattern, a slight, consistent uplift compared to surrounding areas, caused by thermal expansion of the rock above the heat source. But SAR reveals something even more valuable than location. It reveals operational status. A facility that is running produces heat. Rock expands. A facility that is shut down produces less heat. Rock contracts. By tracking SAR deformation patterns over time, analysts can determine whether a facility has been operating or has gone cold. When Iran claims a facility has been suspended, SAR tells a different story if the rock above it is still expanding. During the months before the June 2025 strikes, SAR analysis of Fordow showed consistent thermal deformation patterns, indicating the facility was operating at full capacity. Iran had publicly stated uranium enrichment had been suspended. The mountain said otherwise. The third physics problem that underground facilities cannot escape is the most counterintuitive of all. Empty space weighs less than rock, and the difference, though tiny, is measurable. Gravity is not perfectly uniform on Earth's surface. It varies slightly based on the density of material beneath the measurement point. Solid granite is dense. Empty tunnel is not. A sensor directly above a tunnel, where there is empty space rather than solid rock 50 meters below, measures a very slightly lower gravitational pull than a sensor above solid rock 50 meters below. Traditional gravimeters could not detect differences this small. The signal was buried in noise. But quantum gravimeters, developed using the same principles as quantum computing, measure gravity using laser-cooled atoms dropped in a vacuum. The atoms fall. The rate of their fall is affected by the gravitational field below them. The precision, detecting gravity changes equivalent to finding a tunnel 50 meters underground from a sensor on the surface. Here's what makes this detection method so devastating for bunker security. It requires no signal from the facility, no vibration, no heat, no emissions. The facility can be completely powered down. No generators, no ventilation, no movement. Complete silence. And the quantum gravimeter still maps every tunnel and chamber below. Because empty space always weighs less than rock. That law of physics cannot be turned off. When all three systems work together, seismic mapping revealing what is operating, SAR revealing where heat is being generated, and quantum gravimetry revealing the exact shape of every void regardless of operational status, the complete underground architecture of any facility becomes visible. Not approximate, precise enough to target individual chambers. Every underground facility has one unavoidable connection to the surface: ventilation. People need oxygen. Equipment needs cooling. The air has to come from somewhere and go somewhere. And where air comes from and goes, it carries temperature. Ventilation exhaust from an underground facility is warmer than ambient surface temperature. The facility generates heat. The ventilation system removes that heat by drawing in cool outside air and expelling warm air. At the ventilation exhaust points, which must breach the surface somewhere, the expelled air is measurably warmer than surrounding rock. High-resolution infrared satellites can detect temperature differences of 0.1 degrees Celsius at ground level from orbit. A ventilation exhaust expelling air 3 to 5 degrees warmer than ambient temperature is not subtle. It is a beacon. And ventilation exhausts are not optional, they are structural requirements. Without them, everyone underground dies. With them, the facility announces its location to any infrared satellite passing overhead. Iran camouflaged ventilation exhaust points, placing them inside rock crevices, covering them with debris, disguising them as natural features. This reduced the infrared signature, but did not eliminate it. A rock crevice with warm air flowing through it has a different thermal signature from a natural rock crevice. The pattern of temperature distribution around a disguised exhaust, how the warmth spreads across the surrounding rock surface, is distinctive and identifiable with sufficient imaging resolution. Combined with the seismic signature of the ventilation fans themselves, which have a specific mechanical frequency detectable through seismic arrays, the ventilation system that keeps an underground facility alive simultaneously tells analysts exactly where it is, how large it is, and whether it is currently operating.
Here is what the complete detection system looks like in operation. 4 independent physics-based sensors, each exploiting a different property of the underground facility that cannot be concealed. Seismic arrays map what is operating inside: the generators, ventilation fans, vehicles, human activity. The rock transmits these vibrations whether the facility wants it to or not. SAR satellites map where heat is being generated, thermal deformation of the rock's surface that reveals operating sections versus dormant sections. Quantum gravimeters map the complete physical architecture, every tunnel, every chamber, every void, regardless of whether anything is operating inside. And infrared satellites identify every ventilation exhaust point, the life support connections that no underground facility can eliminate. Each system has limitations. Seismic arrays require the facility to be operating. SAR requires patience, weeks of comparative imagery. Quantum gravimetry requires overflights at low altitude. Infrared works only when ventilation is active. But together, cross-referencing 4 independent data streams, the complete picture emerges, not despite the rock, through the rock, using the rock's own physics against the facility it was supposed to protect. Iran spent billions building facilities underground to hide them from Israeli intelligence. The facilities were underground. The intelligence found them anyway. Not through spies, not through informants, through physics, through the seismic waves that granite conducts better than any other material, through the millimeter-scale breathing of rock above a heat source, through the weight of emptiness that quantum sensors can measure from the surface, through the warm breath of ventilation exhausts disguised as natural rock. The Fordo facility was built to be unbombable. 80 meters of granite, blast doors, redundant power systems, the most hardened military construction in the Middle East. Iran called it indestructible. But before the question of whether a bomb could reach it, came a prior question that Iran had not fully answered. Could the facility be found? Could its internal layout be mapped? Could its operational status be monitored from the surface without Iran knowing? The answer, through seismic arrays, SAR satellites, quantum gravimetry, and infrared imaging, was yes, completely, continuously, without a single Israeli sensor ever touching Iranian soil. You cannot hide behind physics. You can hide behind a rock, but rock conducts seismic waves. Rock expands when it is warm. Rock has mass that empty tunnels do not. Rock allows warm air to escape wherever ventilation breaks the surface. The mountain that Iran chose as its shield was simultaneously and invisibly its most detailed informant. Knowing where the bunker is and what is inside it, that is the first half of the problem. The second half,
how do you destroy something 80 meters underground with a conventional weapon? In Part 2, we cover the GBU-57 massive ordnance penetrator in complete engineering detail. How it penetrates rock, how it knows when to detonate, and why building the unbombable bunker and building the bomb that beats it have been in a race for 30 years. Subscribe to Grand Structures. Part 2 is coming.